Okay, now I will give you an example of a continuous function. The function is given in this way. To give a function, you need to tell us what the domain of definition is and how the function associates the dependent variable to every independent variable. This is what we need to do for determining a function. So, but if I just tell you how the function associates the value at every variable, the domain of definition of this function will be regarded to be the largest set so that everything makes sense. Okay? Now, our function is given in this way. It associates the point xy in R2 to the value by sine x squared plus y squared. This is the function. The domain of definition of this function is R2. This function is defined on R2. Or our function is in fact is this map. Our function is this map. The domain of definition is R2. So I declare that this function is continuous. How to prove this? The proof is very easy. According to the definition, we take pk, this xk, yk in R2, and the pk converts to a point p. Maybe we should take p first. We take p first. We want to show that the function is continuous on R2. We need to prove that for every point in R2, the function is continuous at that point. So for any p in R2, we want to prove that f is continuous at this point p. For this purpose, we take a sequence pk. Suppose the coordinate of pk is xk and yk. Pk in R2 and the pk converts to p. Of course, we can also assume that p is AB. The coordinate of p is AB. So pk converts to p. This is convergence of sequence in R2. By the equivalence of convergence and the component-wise convergence, xk converges to a, yk converges to b, right? So we see that the sine square root of xk squared plus yk squared will converge to sine square root of a squared plus b squared, right? This is the properties of the convergence sequence of real numbers. Okay, so we have this convergence. This sequence of real numbers converge to this sequence, this real number. But the sine square root of xk squared plus yk squared is exactly fpk. Similarly, the right-hand side of this convergence is exactly fp. So we have proved that whenever the pk converts to p, the value of f at pk, the sequence of function value, the sequence of dependent value, fpk converts to fp. So f is continuous at p. Since p is arbitrary, taken from the domain of definition, f is continuous. Okay. Okay, having defined the continuity of function and show you examples of continuous functions, we'll discuss the property of continuous functions. First, a proposition. We know that a function f, vector valued function f can be written in this way by its components. So for the components fi, they are real value functions. Of course, for real value functions, it's simply the case m equal to 1 for vector value functions. So for real valued functions, it also makes sense to talk about continuity. So a natural question is, what's the relations of the continuity of f and the continuity of its components? The answer is very simple and very natural. They are equivalent. So proposition f is defined on A, take value in Rn, and A is a point in A, then f is continuous at A if and only if all the components is continuous. At A. They are equivalent. So the proof is very simple. We prove the only if part. We already know f is continuous at A. We want to show that fi is continuous at A. So for fi continuous at A, what is this means? What does this means? Okay, fi continuous at A means fxk converts to fa if xk converts to A. Of course, xk belongs to the domain of definition A. Okay, so this is what we want to prove. Therefore, we need to consider a sequence converts to A. We take a sequence converts to A, and this is fi, and try to see whether fixk converts to fia. Okay, so the proof. No, maybe take a sequence in A, the sequence converts to A. We want to show that fixk converts to fia. Since f is continuous at A, we have fxk converts to fa. The sequence fxk converts to fa. Now by the relations of convergence and component-wise convergence, we see that fixk converts to fia. Therefore, our result follows: fi is continuous at the point A. So the only if part is proved. For the if part, it's the same. We want to show that f is continuous at A, so we need to take a sequence in A which is converging to the point little a, and try to show that fxk converts to fa. So we take xk in A, xk converts to the point A. Since fi, here I will emphasize that fi is continuous for every I. This need to be true for all I. Here I is 1, 2 for every I. Otherwise, the result is not true. Okay. So since F1, Fm are continuous at the point A. Maybe I write it more clear. Fm are continuous at the point A. All the Fixk converge to Fia. So Fxk is F1xk. Oh, I could not write it here, not enough space. Fmxk. This will convert to F1a, F2a, Fma, which is Fa. So we deduce Fxk converge to Fa for every sequence xk in A converging to the point A. Therefore, F is continuous A. So the if part is also proved. So this is the first proposition of our continuous function. So the result is that a vector valued function is continuous at a point if and only if all its component function fi are continuous at a point. Okay.